PhD at Johns Hopkins, and then you started working as a senior research associate with Herein. So we're very happy today to hear you talk about graph matching, and please get started.
Thank you for having me. So I'm going to talk about information recovery and error-free labeled graphs via graph matching. It's not a very catchy title, but hopefully it'll be catchy work. So the one-slide summary. If you're doing paired graph inference or multiple graph inference, and you assume that you know who's who across the graphs as assumption of your inference task, what effect does that who's who across graphs being shuffled have on subsequent inference? And we're going to look at some examples from hypothesis testing and graph clustering, and we're going to build a model in which we can answer this, sort of tackle this question from an information theory perspective. How much does the errorful correspondence increase the uncertainty between the graphs, and sort of how does that impact subsequent inference? So, and then in theory and practice, we're going to demonstrate that when graph matching, essentially aligning the two networks to maximize common structure, when that can recover the errorful correspondence, then relatively little information was lost by shuffling. You can sort of undo whatever was done. And although relatively little information was lost, that can have a profound impact on inference. And the graph matching can then recover the information and recover the lost inferential performance. So it's sort of an argument for graph matching as a pre-processing step in multiple graph statistics. If you're going to use correspondences across vertex sets, it doesn't hurt to graph match. Okay, and this is going to be focusing mainly on ideas and results from this paper on arXiv. It's not the most readable paper, but I'm more than happy to talk about it with ad nauseum. So there's a lot of examples in paired or multi-graph inference that you implicitly assume that there is an explicit correspondence known across graphs. There's examples in two-sample hypothesis testing for graph value data, and some of the recent papers that have come out doing that assume you know who's who across graphs. There's joint graph embedding algorithms, graph value time series methodologies, non-negative tensor factorization methods, and all of these are implicitly assuming that you know this correspondence across graphs. And there's lots of applications where these correspondences are either unknown or errorfully known. And I think connectomics, which is sort of brain graphs, offers a really striking continuum of this. Because for the simplest organism that they have the connectome for, the C. elegans roundworm, they have the connectome measured under different modalities, and they know what vertex explicitly is what vertex across modality. And so you can leverage the fact that I know what vertex is what across the chemical connectome and the electrical gap junction connectome, two ways of measuring neuron interactions. And I can leverage both of those because I know who's who across them, and joint inferences, we've shown the way to proceed in that space. In human brains, often what we have is DT-MRI connectomes or functional MRI connectomes. And what vertices in those connectomes are, they're not neurons, they're regions of the brain. And the brains all are registered to a common template, and so I know what region goes to what region because it's the same template that you're registered to for all the different brains. And so it makes sense to do paired inference there as well. And you could do things like, given a collection of brains, leverage the entire collection to figure out how to make a test for is the brain from a male or a female. In more complex organisms than the roundworm, though, explicit cross-neuron correspondences are either unknown or errorfully known. And this is an example from the connectomics on brains, and this is sort of the way they make these brain graphs is they take the slice images of the brain and then trace neural fiber bundles across the slices to connect regions of the brain. And this requires incredible computer vision and incredible manpower to do, and is really expensive. And then what they spit out is some brain graph where each of these is a region of the brain, and they're connected if there's fiber bundles connecting the regions. And there's errors all across that, where the computer vision may lose a fiber bundle or may pick up extraneous fiber bundles. And going at it from a actual neuron level is way beyond our capabilities right now. I think we have partially reconstructed neuron level connectomes of flies. And I've been told that to get the full one, we need to wait 10 more years and infinity money from the people building them. So, okay. So, and if I have this errorful correspondence, what effect does that have on what I'm going to use the graphs for? And here's a simple example from hypothesis testing. And this is from a 2-sample graph hypothesis test that we put out in 2014. And if I want to test in 2 random dot product graphs, which is essentially given x, G1, the edges of G1 are independent draws from the matrix XX transpose. And so X has restrictions, it has to be between 0, the XX transpose is between 0 and 1 and so on. But if I have 2 of these graphs and I want to test, are they from the same distribution or not? Or is the X the same or not? And the same is again up to rotation because we have a non-identifiability concern there. As vertices get shuffled, the power of our test decreases precipitously. And so we're sort of implicitly assuming in our test that we know who's who across graphs, and as that becomes more and more errorful, our test becomes essentially rubbish. The power drops to 0 relatively quickly. In these graphs, I think I had 90 vertices, so at about 60 vertices shuffled, the test isn't even valid anymore. And as a second example, I'll consider joint graph clustering. So if in the C. elegans example, I had 2 connectomes measured under different modalities. They're giving us different information. And so can I leverage both of them together to jointly cluster the neurons into neuron types? There are motor neurons, there are sensory neurons, and there are interneurons. And they have different functions in the brain. And if I want to find what neurons are motor neurons, having the information from a chemical and electrical connectome is useful. And this is an example of if I jointly cluster the graph, sort of leveraging the signal across both graphs, and this is a joint clustering method that we came up with in 2015. Leveraging the signal across both graphs, do I gain something? And this is the ARI, which is a measure of cluster validity. If I had just taken the chemical connectome, embedded it by itself, clustered it using 3 means clustering, that's my ARI. If I had then taken the joint graph, embedded that and clustered it, my ARI is significantly higher than if I just use one graph by itself. So I'm leveraging the information contained in each connectome sort of simultaneously. As I shuffle things, and Omni's just our method of embedding, as I shuffle things, you see that the gain obtained by using both graphs vanishes. And that makes sense. Sort of, I'm losing the information in the labels across the 2 networks. And if I then try to unshuffle them by what I call graph matching them, and I'll get to what graph matching is formally in a few minutes, then you can see sort of I can recover the lost gain, at least up to a point. If they're too shuffled, I can't even align them with graph matching just because it's a really hard problem. So in this example, you see that shuffling can have a dramatic impact on inference. Graph matching, or essentially aligning graphs to minimize the edge disagreements or maximize the common structure, that recovers the true correspondences and that can recover the lost performance. And so if people have heard the words graph matching and think of like pairing vertices across graphs so that you make like essentially a large bipartite subgraph with them, I'm not meaning that. I mean this. And I'm not meaning that because, well, this was written before this reference is years before I was born. And so there's precedence from before I was born to call it graph matching. And so I won't break that. But this is a paper from 2004 called 30 Years of Graph Matching and Pattern Recognition. It's a really off-use tool in computer vision and statistical pattern recognition. There's since been a paper that came out in 2014 called 10 More Years of Graph Matching. And so it's at least 40 years old, which is older than me. Okay, so what do I mean by graph matching? If I'm given two graphs, G1 and G2, with respective adjacency matrices A and B, the graph matching problem is to minimize over permutation matrices P, AP minus PB in Frobenius norm. It's essentially relabeling B in order to minimize the Frobenius norm between A and relabeled B. It's very similar in flavor to the graph isomorphism problem. The difference is I'm not asking are they the same, I'm asking find the thing that makes them the most same. It's harder in that way. I won't probably get to it, but that is the same problem in that it has the same argument as if I minimize the negative of this trace formulation. And this plays a significant role in how we actually solve graph matching, and hopefully I'll at least mention that as I go. Here's a quick example of two graphs that I'm matching. If this is G1 and this is G2, and these are their adjacency matrices, then I'm sort of aligning the adjacency matrix of G2 to match G1's adjacency matrix as best as possible. And this shows the overlay of the two, where gray edges are edges that are only present in one of the two, black are edges that are present in both, and white are edges that are absent in both. And you can sort of see I've captured a lot of the structure common to G1 by relabeling G2. Okay. So the question that we came at this from was, how do you quantify the effect of added uncertainty due to an errorfully observed vertex correspondence? In some sense, this is the antithetical operation to graph matching. If matching is aligning things correctly, shuffling would be unaligning them. And how do you capture the added uncertainty due to the shuffling? Heuristically, if you have G1 and G2, and they're a realization from a bivariate random graph model, with the property that vertices aligned across graphs behave similarly in their respective network, if I observe G2 or G1 and the alignment, then the uncertainty in G2 is greatly reduced. You can think if they're actually isomorphic graphs, then if I observe G1 and the alignment, then G2, I know exactly what's happening with it. If they're independent, well, the uncertainty may be reduced depending on the structure of the networks, but less so than isomorphic. So, and as I shuffle the labels, additional uncertainty is introduced into this bivariate model. Sort of I'm saying that vertices that are no longer statistically the same are behaving statistically similarly, and that's adding uncertainty into my predictive abilities. How do I quantify this? Well, to formalize this heuristic, I thought information theory seems the most natural avenue, and it's exactly getting at the added uncertainty of, given G1, what the added uncertainty in G2 if I observe both. So we adopt an information theoretic perspective and develop a bivariate graph model, which I call row correlated stochastic block model. And it allows us to answer the questions, what is the information loss or increase in uncertainty due to shuffling? How does this information loss impact subsequent inference? Can graph matching recover the lost information? And it turns out that this we have a handle on, this we have a handle on, and this has stumped us. And that is pretty sensical because actually quantifying the effect on inference is quite challenging. Okay. So what's the row correlated stochastic block model? We say a bivariate random graph is row correlated stochastic block model with parameters k, n hat, b, and lambda. If each one marginally is just a stochastic block model with parameters k, n hat, b, and lambda. And essentially what that means is that lambda is a matrix that says the vertices are going to be split up into k communities. Lambda is going to be a k by k matrix that says what's the probability of a vertex in one community communicating with the vertex in another. For each I equals 1, 2, the vertex set is partitioned into k disjoint communities. The block membership function denotes which community you're in. So V is in the community denoted by, indexed by BV. And for each pair of vertices, and I'm dealing with undirected SPMs, for each pair of vertices we have that there is an edge between them independently with this probability. It's the Bernoulli random variable with parameter lambda with the associated block parameters indexing it. The associated blocks indexing it. Okay. So what makes row-correlated SPMs more general than regular SPMs? Well, in row-correlated SPMs, the random variables collectively across graphs are independent. The existence of edges collectively are independent, except that for the same U and V, the correlation between an edge between U and V in graph 1 and an edge between U and V in graph 2 is rho. And so it essentially edgewise correlates the two graphs. It's the first correlation structure, perhaps the simplest correlation structure to consider.
Let me just check here. So you have the same partition of vertices for both
Yes.
graphs?
Yes.
Yes.
It turns out if we have different, we can correlate graphs that don't have the same distribution,
Okay.
but it restricts what row could be.
Okay. Yes.
But for this, yes, they're both from the same, they have the same partition. Note if lambda's constant P, our block probability matrix is constant P, then we're just in the Erdős-Rényi setting. And our initial work on graph matching was in the row-correlated Erdős-Rényi world. We can easily generalize our model to what I call row-correlated Bernoulli graphs, which is the most general edge-independent random graph. Essentially, the existence of every edge is its own parameter, and there's no block structure at all. We have nice theory in this world. In this talk, I'm only going to focus on row SPMs because they're easier. And I'm working on generalizing things to row-correlated Bernoullis, but things get more difficult. In some sense, though, the Erdős-Rényi is the graph with maximum entropy amongst all the Bernoulli random graphs. And so proving matching results in the Erdős-Rényi setting should immediately go to the general independent edge graphs. We just have no idea how to do that. So we have convinced ourselves it's a result that once proven will be trivial, and we just have no idea how to prove it. So in this row-correlated SPM model, it has a really nice function, in that if we're talking about graphs with a latent alignment, if I'm asking what is the permutation matrix that maximally aligns A and B, where A and B are the adjacency matrices of my row-correlated block model. If rho is 1, then the graphs are isomorphic, and asymptotically, almost surely, the optimal relabeling is the identity. If rho is 0, the graphs are independent, and asymptotically, almost surely, the optimal permutation is not the identity. It's pick your favorite one, and there you go. This model allows for G1 and G2 to have a natural vertex alignment, namely the identity function, for rows strictly between 0 and 1. So for 1, the alignment is very sensible because it's isomorphism. For 0, there is no alignment. But for rows between 0 and 1, now we have an alignment due to the statistical similarity of vertices across graphs. Okay, so the first question we asked is, okay, if we have this model, how do we quantify the effect of added uncertainty due to an errorfully observed vertex correspondence? Now, you can say if all my parameters are fixed, so I'm in the simplest setting where my block probability matrix is fixed, the number of blocks is fixed, and my correlation is fixed. I can ask, what's the mutual information between G1 and G2? And it happens to be theta of n squared. It's easy to compute what the actual value is. Because they're independent edge graphs, you can just work edgewise. In the setting where my correlation is going to 0, and my lambda and my k are fixed, so this is sort of sweeping between completely the same isomorphic to independent. This is the lead order of my mutual information. It grows like rho squared n squared as n goes to infinity. Okay. And so how, if I were to take G1 and I were to shuffle the vertex labels of G2, what impact would that have on this mutual information? To do that, I needed to think of a way to actually formalize the notion of shuffling two graphs. Okay, so this is a really long named definition, but it's quite simple what it's actually doing. So we have sigma shuffled, row correlated stochastic block model graphs. And again, we're not the best at thinking of clever names for things. This is a very self-descriptive name. If G1 and G2 are themselves row correlated SBMs, and if I look at any x, y in script Gn cross script Gn, where script Gn is the set of all labeled graphs on n vertices, the probability that G1 equals x and sigma G2 equals y would be, well, I sample a permutation from sigma, and then I ask, what's the probability that G1 was x and G2 was phi inverse of y? So if I were to sample a permutation from sigma, I would ask, what's the probability of sampling G1 and G2 such that when I shuffle G2 according to phi, I get back y? Okay? And so you first sample phi from sigma, then independently sample G1 and phi G2 as row SBMs. We know the distribution here, those are just row correlated stochastic block models. So the first theorem that we have is that if sigma is the uniform shuffling on the vertex set, so if you have sort of maximal entropy in your shuffling, what's the information loss? And you can show that if the correlation is relatively large, so if the correlation is of little omega of root log n over n, then the relative amount of information you lose is small. You lose something, but relative to how much you started with, it's not much. I can show that this upper bound is not trivially zero. It's big omega of n rho squared, which does go to infinity, so you have lost something. It's just what you've lost is relatively small. I conjecture, and Carrie might disagree with this conjecture, but I will conjecture that in the very low correlation setting, the amount of information you lose due to shuffling is large. And I have some evidence for this, and I'll talk about sort of what that evidence is as we go. So, given this conjecture, I have like a phase transition in the amount of information loss depending on how much correlation is present in the two networks. So, in examples though, even with modest correlation, the lost information dramatically can impact subsequent inference. And so here's that example again from hypothesis testing, where I actually correlated the two graphs with rho equals 0.4. So they have a fair amount of correlation between them. And you can see that even the little information that's lost dramatically decreases the power of the test. If I come in and then graph match these two before computing my test statistic and use that to test whether x equals y, that's what happens. With matching, I recover much of the lost inferential performance. And if you're sitting there, you're saying, but this is, what is that? That's an algorithmic artifact. Matching is NP hard in general. There is no way to match perfectly. And so we have an algorithm that happens to work really, really well in practice. It seems to be state of the art. And even in this setting, if you've shuffled enough, you can't recover the true alignment. If I had an Oracle graph matching algorithm, or like infinite time and a really nice computer running Garobi, the plot would look like this, where this would be a straight line across, and I would recover the power as though I had shuffled nothing. Okay. In the joint graph embedding story, we have sort of a similar phenomena happening. These are now row correlated SBMs. They have 3 blocks, and I want to cluster them into 3 blocks jointly, sort of leveraging the signal across the matrices. If correlation is 0.5, you can see that if only using G1, so spectrally embedding G1, running 3 means on it, 3 means clustering on it, that's my ARI. I do fairly well. Here I used shuffled vertices as my x-axis. Here I'm using seeds as my x-axis. Forgive me, seeds are the opposite of shuffled vertices. So a vertex is a seed if it's not shuffled, and we know that ahead of time. So in your mind, if you can transpose those, I couldn't on my computer. We can see that coming from this direction, as I shuffle more vertices, using our joint embedding procedure without matching, my power goes down precipitously. And if I first match them and then do my joint procedure, I recover all my performance, except here, again, that's an algorithmic artifact. And again, here, that's an algorithmic artifact. Note that the amount of gain I get in the 0.5 setting versus the 0.7 setting is meaningful. Because if I want to leverage signal across two graphs, essentially the worst case scenario is if the graphs are isomorphic, because there's nothing to leverage. If I have one, it might as well give me, I have everything. And as correlation increases, the graphs are introducing less helpful signal in the bivariate model. And so with correlation 0.5, I have a better gain in inference versus correlation 0.7. So this story, so far, the first part of it says, shuffling hurts you, graph matching helps you, but how on earth do we formalize the notion of graph matching helping you? So far, we have a theory that says shuffling can hurt you. Can we get the same sort of theory to tie the story together with graph matching? And the answer is yes, and here's the theorem. So in that high correlation setting, where rho is little omega of square root log n over n, almost always I get that the optimal permutation according to graph matching is the truth. So if I had an oracle graph matching procedure, the probability of this occurring is exponentially large. And so for a sufficiently large graph, if I could match them, I would get the truth back with really high probability.
If you could computationally?
Yes, if I could computationally, if I had an oracle procedure. So this says essentially graph matching can work. In that low correlation setting, where we have a correlation as little o of root log n over n, this essentially says that graph matching can't work. The probability that you can recover the identity by optimally matching is going to 0. I actually have, the result is slightly stronger in the paper. I used the little omega and little o notation for symmetry here. But I have that there is a constant such that if you're bigger than a constant, root log n over n, this holds. And there's another constant such that if you're less than that, this holds. And the constants have a gap. And I don't know what happens in the gap. But you could spend lifetimes chasing phase transitions, which is a pretty good lifetime. Okay, and if you remember, this is the setting where relatively little information was lost. And that intuitively makes a lot of sense. If somehow you can undo the shuffling with a pre-processing step, then it makes sense that you didn't lose much in the shuffle. And I conjecture that this is the setting where relatively significant information is lost. If you shuffle and can't undo that shuffle, then you've lost something. I don't know how to, as I said, this is a conjecture. I don't know how to prove it yet. If you have ideas, I'd love to hear them. But I have some evidence, and I'll talk about the evidence in a bit. Okay. So we've teased out a phase transition and matchability, and given the conjecture that corresponds to the phase transition and information loss. How do we define the act of matching in a random graph model? So I know how to say what's the probability that I'll get the right alignment, but how do I talk about the aligned graph? If you think about it for a few minutes, there's only really one way to define it. I mean, there's infinitely many ways, but only one way I can think of. And this, again, that might not mean it's the right way. Probably doesn't. So if I have the G1 and G2 are just XY, they're just deterministic graphs, then how do I define G2 aligned to G1? Well, it makes sense to say that any graph that if there is an optimal permutation aligning G2 to G1, and I apply that permutation to Y, any of these Z's should be equally likely. Sort of any optimal permutation according to the graph matching algorithm, when you use that to relabel Y, that Z should be what you define the matched G2 to G1 to be. And there can be more than one of those, and any one equally likely. So heuristically, this set P star y matched to x is the set of optimal relabelings of y to align y to x. Okay? And now, in a random graph setting, if I have this row correlated SBM setting, I'm not putting any shuffling in here for the time being. The probability that G1 and then G2 matched to G1 equals XZ would be the probability that G1, G2 equals XY, where Z is an optimal relabeling of Y, divided by the probability you actually chose Z as your optimal relabeling of Y. And that's a perfectly good probability mass function. It defines this as a bivariate graph-valued random variable. And one of the beautiful things about this is I haven't shuffled anything. But shuffling and graph matching are in some sense antithetical operations. And so the probability if I first randomly shuffle G2 and then align it to G1, that bivariate random variable is equal in distribution to if I didn't shuffle anything to begin with. And that's beautiful then because we can sort of study this by actually building a tractable definition here. And we show that in the high correlation setting, the information that you lose by shuffling, now this is not relative, this is absolute, does go to infinity, and you can check if I square rho and multiply it by n, I'm little omega of log n, so it is going to infinity. And if I shuffle G and then match it to G1, the information I've lost is little of 1. So I've essentially recovered all the lost information by shuffling, all the information lost by shuffling by matching. Okay, and this is an immediate consequence of Fano's inequality. So graph matching does recover the lost information. And this gives us a nice intuition, theoretical intuition behind sort of the empirically observed phenomena. We've empirically observed that when you match things that have been shuffled, it helps with the performance of inference. And inasmuch as the inference depended on the information between the random graphs, graph matching recovering the lost information makes sort of that empirical observation, it puts it on solid theoretical footing. Now, I'll quick sketch the proof of the theorem. The proof is it was one of those things that it's not hard once you see the right way to do it. And I think the proof is instructive because it sort of lets you see one way to view our row correlated model. So in the row correlated setting, one way to view the model is I first sample A, I first sample G1, and then conditional on G1, I can choose to keep edges independently in G2 or not. And the probability of keeping the edges is dependent on the probability the edge was there in the first place. But I can sort of realize my graph in this two-phase procedure. First sample G1, then flip bits in G1 to get G2. And we can show that the number of excess errors due to a shuffling versus if I had used the true correspondence is equal to the number of excess errors if I were to have shuffled B, just shuffled one of the graphs, and then condition on that graph, I have to subtract out the errors I'm correcting by bit flipping. This is conditionally independent. I mean, we condition on B, and this random variable conditioned on B is independent of that. And so we can tackle this via a two-phase concentration inequality, via sort of two-step concentration inequalities. We can, and here's the way you realize it, condition on B, edges in A are Bernoulli probability, or essentially either Bernoulli with this probability if the edge is present in B, and Bernoulli with that probability if the edge is not present in B. And using a sort of delicate concentration inequality, we can show that if the number of errors you induce by shuffling B is large, then the probability that you've corrected too many errors is small. So if you make a lot of mistakes, the only way that the shuffling could win is if you correct a lot of those mistakes. And the probability of correcting the mistakes is small, conditioning on making a lot of mistakes. Then it was just a matter of figuring out how many mistakes you'd make within each block and across each block and sort of delicately putting that all together to say that this is large with high probability. So that's how we proved, and then you use a union bound because the concentrations are exponentially, we have exponential bounds in the concentration, and you can just use a union bound to show that over all permutations, shuffling will induce more errors than not shuffling with high probability. The sketch of the second half of the theorem, I think, helps build intuition behind what can go wrong in low correlation settings. So in low correlation settings, is it that the graph has a sort of a permutation of all the vertices that's causing a global alignment to be better than the identity function? And the answer is no. The answer is, if you're going to lose by a little, and as rho goes down, what a little is grows. So as rho is 0, there will be one that shuffles everything that beats you. And as rho sort of gets to the phase transition, you're not going to be able to win except by like a transposition or a k-cycle. And so we consider the set of maximal disjoint within block transpositions. Again, rather wordy, but it's essentially disjoint transpositions in that they're transposing different vertices within block and that we're never messing up things across blocks. And if we count how many of those beat the identity, so how many of those are better permutations than the identity, and we call that x, it's pretty easy to get that the expectation of x has that growth order. And the question is, well, how do you get at a second moment of this? And the second moment gets delicate because there is covariance in each of the individual summands of x. But you can sort of ignore the covariance and then do some delicate bounding and say that the ignoring was okay. And you get that the variance of x is this order. And so it's a simple application of the second moment method to get the probability x is 0 goes to 0. So with probability going to 1, some transposition will beat the identity. And the same exact proof works for disjoint k-cycles, if k is finite. For k going to infinity, you run into issues at the rho equals sort of essentially just a little bit smaller than root log n over n. So I think maybe the most interesting thing here is the low correlation regime. I don't understand it. And to me, that makes it fun. So what's going on in the low correlation regime? And this is the realistic regime. Because if you're thinking of this as an actual inference tool, if I have, say, 2 social networks and I want to figure out who's who across Facebook and Twitter, the correlation across those 2 might be very small, and there might be sort of vertices that are present in one and not in the other, and all sorts of different errors. So this low correlation regime is sort of the realistic setting. This is an example of what happens if I were to match in the low correlation setting. This is if I take our algorithm and I start it at the true labeling across graphs. Now, if the algorithm doesn't move, it means the true labeling is the right thing. And if the algorithm moves, it means that there's something better. And you can see that this is correlation in a log base 2 scale. As the correlation drops, you can relabel B and get a better, less errors than if you were to have used the true alignment. Those are actual error bars. So you have tight concentrations here. It turns out in the SBM setting, you can use central limit theorems to show that these things have to be normal with very high, and the variance goes to 0 very quickly. So we have, you win by shuffling, but you don't win by a whole lot. And if I were to have shown you sort of this is in the tail of the distribution, and sort of there's another point down here that would be sort of a similar tail, and that's sort of where you're bounded between. Now, although you don't lose, I conjecture that in this low correlation setting, you lose a lot of information, and you can't get it back. but you can get something. And so I can't recover the true alignment, but I can still get some of my inference that I lost back. And this is sort of what I view as the rainbow behind the rainstorm. Because if the case was I can't ever I can't ever align these graphs correctly, and I can't ever hope to recover anything, well then, thanks, and I should probably have not pursued this line of joint graph inference, because it's impossible. But here I'm saying that in this, this is again the picture from the C. elegans, in that graph, even with 150 seeds, our algorithm, which is better than sort of all the other algorithms that have been run on this data set, only gets roughly 15% of the vertices correctly labeled across graphs. And these have 300 vertices roughly each. And so if you use half of them and you say, I know who's who, find the other half, we only get roughly 15% correct. But we're getting some structure there. We're aligning the two networks in a way that's structurally better than the truth. And that structure that we get really helps you when you're doing joint clustering. And it really helps you if you're doing something like joint hypothesis testing on the C. elegans. And so here you can see that when I do match, this is 150 seeds, so I'm only getting 15% correctly aligned across graphs. I'm still doing better than if I had used one graph by itself. And only down here when sort of the algorithm just horribly breaks am I worse than if I only used one graph. Figuring out this point is difficult, but we're working on it. And in this regime, I conjecture that something is actually lost in the shuffle. And I have some idea of sort of what would be lost in the shuffle. And I think it's going to have to be a matter of the information contained across the graphs decomposes into information that's sort of between edges and information that's more structural to the model. And the information that's more structural to the model can be recovered, but the information that's between the edges is lost. And in a thing like clustering where you're after gross structure, it makes sense that the information you can recover, being the structure, helps your algorithm's performance. It turns out that if I have independent SBMs, so rho is 0 now, and if I were to ask, well, the information between them is 0, but what's the information if I match G2 to G1? So what's the information if I optimally align the two independent SBMs? And it turns out to be theta of n log n. And that is n squared times the phase transition. So matching independent graphs brings me to the correlation level of matchability, which makes sense because if I've matched them, then those are matchable because they're matched. And if I were to shuffle them, I would get that same matching back with high probability. So it brings me to the phase transition of matchability. And intuitively, I think, if I were to shuffle this, I would get back to them being independent. And sort of at the phase transition, shuffling almost creates independence amongst graphs. And this is a heuristic, I don't have a proof. Heuristically, graph matching correlates graphs. And if they're independent, it sort of correlates them more than they would have been naturally. And shuffling uncorrelates dependent graphs. If I have dependence there, and Carrie vehemently disagrees with me here. If I have dependence there, shuffling essentially uncorrelates them. It reduces the dependence. And it's a nice way of viewing them as these antithetical operations. So, okay. I have 66 slides, so I could go on all day.
Good runners would end 5 to it.
Yeah, no problem. So, rather than go through this example, I'm actually going to go to some future work. And then I'll talk about sort of a little bit of how we actually match graphs. So, what we're working on now is take these results that we have. And in our model, we have row correlated SBMs, which it's a nice model, but we want more general models. And so how do we lift this to row correlated heterogeneous Erdős-Rényi? So edges now have probability Pij of edge between vertex I and vertex j, and Pij doesn't have to have any structure to it. We know in that setting, the mutual information between G1 and G2 has that same lead order as it did in the SPM setting. It grows roughly like n squared rho squared. And so we can still compute the mutual information there. The question is, what happens if we shuffle and things get a lot more difficult in that setting? There's not symmetry we can exploit in the proofs. So in testing, it turns out that in the hypothesis testing, in the example I showed you, shuffling hurt your performance. When you shuffled, you lost power. And that was for one particular element in the alternative, one particular y that did not equal x. It turns out, and this is something that none of us so far understand, and I think it was like we have a 6-month-long email chain where we're all trying to understand it and none of us are coming close. It turns out for some other elements of the alternative, shuffling helps you. So if you shuffle the graphs, the alignment of the vertices, and this is in the correlated setting, so there is common structure in the alignment. If you remove that common structure and shuffle, you can get a better fit by shuffling for some members of the alternative. And it turns out that matching lowers the power in those settings. We have that in some settings, shuffling hurts you and matching recovers the power. And in some settings, shuffling helps you and matching hurts you. We don't know, in practice, you have no idea if things are shuffled or not. And so it's a pretty good idea to always match beforehand because it's the conservative, robust approach to testing. If you had a way of characterizing whether something was shuffled and you could figure out exactly how to divide your alternative space into places where shuffling helped and places where shuffling didn't help, that would be ideal, and we are working on that right now. I think that's going to have to do with this decomposition of what information is lost and what is kept, and sort of how shuffling can either remove nuisance information, and matching would be recovering that nuisance information, and vice versa. Okay. The next thing we're working on is the correlation structure that we have is it's edgewise correlation. And how do we generalize that to more of a structural correlation? So a neighborhood-wide correlation, or even more general than that. And we have some initial definitions of sort of more general correlation via stochastic neighborhood similarity. And we're proving recovering the same results under the more diffuse correlation models. And in a lot of applications like social networks, it makes a lot of sense to have the correlation be my neighborhood in one graph and my neighborhood in the other graph are correlated versus edges are correlated. Because I know a lot of people who are friends with their mother on Twitter, but not friends with their mother on Facebook, and vice versa.
I wonder why.
Pornhub's big in Britain right now.
I don't know anyone who's friends with their mother on that.
There you go.
And the last thing that we're working on is to connect the idea to the graph matching world to the ideas from differential privacy. In some sense, that phase transition of matchability is you can think of as a phase transition for anonymization. So when are networks truly anonymized? So if I have two networks, if I can just recover who's who across the networks, then there's no anonymization there. And if I can't recover who's who, then the networks have effectively been anonymized. Figuring out how to get that sort of anonymization in more complex models and then relating that to the differential privacy, I think is going to be really fruitful. Okay. So in the last 5 minutes, I'll say this real quick. So how do we actually graph match in practice? Well, we have an algorithm and we call it the FAC algorithm. We're terrible at acronyms. It's fast approximate quadratic alignment, not frequently asked questions. But as you can see, I mean, I guess Joshua might be the one who's terrible because he wrote a paper with the GLAG algorithm, which is group lasso adaptive graph matching. Path is, they scooped us with naming. And a common approach to actually matching graphs is you say, okay, I have this combinatorial permutation structure I'm optimizing over. Let's relax things. Let's relax to the doubly stochastic matrices, and now I'm pursuing a quadratic optimization over a convex set, and I have something I can do. Our approach was to say, okay, well, with permutations, this formulation and this formulation were equivalent. They had the same argument. And what we did is we said, let's use this formulation. We're going to use the trace norm formula, the trace formulation, and we're going to use the relaxation of that and use some pathfinding, gradient descent algorithms to find an optimal solution to that. It turns out that these relaxations and the one that's sort of commonly used in the literature are no longer equivalent. This one's convex and quadratic, and so you can sort of hit the relaxation with a efficient algorithm, find the optimal point, and then work your way back to the permutation. This one is quadratic and indefinite, and so we've made a hard problem into a hard problem. But, and when we originally wrote this paper, people were like, why on earth did you do that? You've made the problem into, no one knows how to solve indefinite quadratic optimization. But our thing seemed to work better than all the others, and we had no idea why. It turns out that, and this is saying it works better. Yes, it turns out that with that indefinite, with that relaxation, the optimal doubly stochastic solution to the relaxed problem is still the identity. Whereas, and this is in a row correlated Bernoulli setting, so sort of the most general edge independent random graphs. When you relax our indefinite formulation, you still get the optimal permutation if you could solve it. And when you relax the quadratic, you don't get the optimal permutation. You get an interior point solution. And in practice, we've seen that the interior point solution doesn't even have to be in the Voronoi cell of the right of the optimal permutation. So you get something interior that is often wrong. Whereas ours is impossible to solve, but you get something that's right. This is easy to solve and wrong. And graph matching is NP hard, so I'm not surprised by this. And when you solve our algorithm, here's sort of, I'll end with this. This is an example from what's called the QuackLib dataset. And this is the, we didn't make this. This is quadratic assignment problem library dataset. And this is a bunch of benchmark problems for solving the quadratic assignment problem. And in the most general form, graph matching is nothing more than a quadratic assignment problem. I'm relabeling the vertices of one matrix to optimally align it to a second matrix. And these are sort of 16 benchmark hard problems from the QuackLib dataset. And they're benchmark hard, not chosen by us, chosen by the people who invented the path algorithm, and that sort of was the standard algorithm for years and years and years. And if you see, these are the names of the problems. This is the optimal solution. So this is the, for how the optimally, what is A minus PB P transpose for Frobenius norm squared, what's the best you can do. This is if you just solved the convex relaxation and projected it back to the permutations. This is if you had solved GLAG, if you had used path. And then these are our two solutions using two different initializations. Turns out that our way of solving this is so much faster than the other two, we can do tons and tons of initializations and still have time to go get a cup of coffee. Bold means it's the best performing algorithm, and we were actually quite surprised that our thing performed best in every single example. And in this example, it performed best by, so 16,000 is the best, and sort of the second best is 19,000. So we've gotten a fair amount of relative improvement, like 15%. Here, the best is 11,000 and the second best is 16,000. So we've gotten like a 33% relative improvement, pretty good. Every single one we did the best on. And these problems don't have an optimal alignment between, these problems don't have a natural alignment between them. These are sort of the hard problems of quadratic assignment. And when we do have an optimal alignment, when there is a natural alignment, like in the worm brains in other data sets, we still get the best solution. I won't show those because I'm out of time. So, questions?
Okay, do we get to give you a round of applause before we ask questions?
Depends on how he does on your questions.
Yeah.
Questions?
Yes.
Yes. So you start with a stochastic block model. So do you keep the probabilities there fixed and just vary your row, or are your results here also uniform if you, I mean, you do this for interesting things when row is small here, going to zero at some rate. So can you also let the probabilities P go to zero at more or less the same rate? Or?
We can have rho and P dropping to 0. I'm trying to remember the exact thing. I think it's something like rho times if you have a lower bound on, or a bound on the entries of your lambda.
Yeah, so
Rho,
say you take the Herein case to make it.
Yeah. We have in that setting, rho times P has to be at least of this order to get the matching, and if it's less than that, you can't.
So it's
So
really
we-
row P.
Okay.
Yeah, it's, in this setting, dealing with rho P, we can, it just, the paper was already 47 pages and I didn't want to make it longer. In the general Erdős-Rényi setting, so, yeah, this setting, where it's a generalized Erdős-Rényi, no, that's that setting. What we're thinking is going to have to happen is it's going to be something like a Hadamard product of lambda and rho and some sort of norm condition on that. And we think it's going to be something like that has to be positive semi-definite, and it has to have like one eigenvalue that's big enough, and that's enough to get the matching correct. That works in the Erdős-Rényi and SBM setting, and that's sort of how we think structurally it'll have to work here as well.
If you take a independent stochastic block model,
Yes.
so rho equals 0, and match, you find the matched vertices are basically in the same block and otherwise random.
No. Yeah, I mean, yes. I mean, yeah, otherwise random.
Right. But in the same block. And so there you can see that even though rho is 0, you recover something useful, potentially useful, that is, that the two guys are in the
Yeah,
same
and so
box. That's a hint of the decomposition.
It hints at the decomposition exactly. And I'm happy you said that, because what's the entropy of a random shuffle?
One of random. 17. 5 to the E.
Flag.
What's the entropy of a random shuffle? Hold on, I'll get to this point.
Probably not
Hold
17.
on. What's the entropy of a random shuffle?
And log it.
Yeah. And so I think that this,
Yes, and log it.
the phase transition, I think it's going to be due to the entropy introduced by the random shuffle, if that overwhelms the information contained between the models or not. Because if in the high correlated model, the entropy you introduce is only of order n log n, but the information is of higher order than that, so you sort of haven't lost enough.
Okay, any more comments, or do we have more interesting sounds coming from the side of the room? No? Okay, let's thank you once again.